So this is enzyme kinetics. As you've seen from the video or from the slide, enzyme kinetics is the study of chemical reactions that are catalyzed by enzyme. So this helps us to know whether the enzyme is fast, slow, whether it's spontaneous, whether it needs cofactor or the other. This gives us a proper definition of what of the properties of the enzyme. From the equation above, you see enzyme plus substrate will give us enzyme substrate complex and will give us enzyme, and finally give us enzyme products. You can see the substrate approaching the enzyme active site, then you can see there is a binding that which forms the complex, and eventually the product is being released, whereby the enzyme goes back to its native state. So this is the basis of how biological reaction takes place. It takes place because there must be a point in time whereby enzyme substrate complex must be formed, and when it is formed, it will eventually lead to product. For every of the reaction, when the rate at which your enzyme substrate is formed, that's the rate at which product there is product formation. So when the enzyme substrate complex is slow, there's a slow formation of the enzyme substrate. That means there will be a slow formation of products. Now this leads us to gives free energy. Now in physics, when you discuss what is energy, energy is your is the work done per unit time. And so for this reaction, what's the energy of this enzyme? The energy of this enzyme is the number of substrates it's able to convert per unit time. So it expresses the energy capable of doing the work during a reaction at a constant temperature and pressure. And how do we calculate the energy? We can calculate it using this formula: delta G equals to minus RT ln KEQ. Then our KEQ is our equilibrium constant, whereby we have enzyme product over enzyme substrate. And so at the end of the day, I told you the enzyme, the concentration of the enzyme and the enzyme will cancel each other. Now below is an example of this for to calculate these variables that we want. For example 1, the conversion of 1 millimolar glucose 1-phosphate to 19 millimolar glucose 6-phosphate at 25 degrees Celsius and pH of 7.0 is catalyzed by phosphoglucomutase. From this data, calculate equilibrium constant, 2, standard free energy, where R is your gas constant and T is your absolute temperature. I've told you in the exam hall, don't bother about the gas constant or the temperature. All these will be supplied. I'm going to supply them, but all what you can do for me is make sure you come to the exam hall with your respective calculator. Now as you can see, the problem addresses that we should find the equilibrium constant and the free energy. Now you can see the reaction below. So this leads us to the equation below. That's the equation of the delta G, which is the free energy, and KEQ, which is the what they call it, which is the equilibrium constant. So all what you do is to first of all find the equilibrium constant, which is the product over the substrate, and that's why we have glucose 6-phosphate over glucose 1-phosphate, and that's 19 divided by 1. Yeah, so the value will be 19. That means our KEQ is 19. Then to calculate the energy, then we use this free energy formula, which is delta G minus RT ln KEQ. Then you put ln 19 inside the bracket. The answer equals minus 7.3 kilojoule per mole. So don't forget the negative sign there. Ln 19 will give us positive sign, and positive times negative will give us negative. So positive times positive or negative times negative will give us positive. So we should be mindful of that, except if we have a negative coming from link KEQ, that will only negate the presence of the minus before the value of the gas constant and the temperature. Then when the energy is negative, it shows that the reaction it shows that the reaction can go forward. But when it is positive, it shows that the action, it needs to be what they call it, joined with another reaction in order for it to be pushed forward. And to calculate the Michaelis-Menten equation, we need to have some variables. As you've seen that this equation, given equation here, is similar to the one which I've shown you, which shows that enzyme plus substrate will be with the reversible reaction will give us enzyme substrates to which we yield to enzyme plus products. Now, what are the variables important for this Michaelis-Menten equation? We have the data, we have the concentration of ET, which is total concentration of enzyme, and X, which represents total concentration of substrate, while ES is the concentration of enzyme substrate complex that is formed. So to calculate the total enzyme use, that means the enzyme equals to enzyme, the free enzyme equals to total enzyme minus enzyme that binds to the substrate, that is enzyme substrate complex. And so once you are able to subtract the total enzyme from, you subtract the enzyme that bind to the substrate from the total enzyme, you'll be able to know the enzymes that do not partake in the reaction. So having understood these variables, it is now then easy for us to be able to calculate the variables that will give us important information about our enzymes. And for us to understand this kinetic Michaelis-Menten equation, it is very important for us to maintain this assumption that there is a constant steady flow, that is steady formation of enzyme substrate that will eventually lead to product formation. Like I said earlier on, without the formation of enzyme substrate complex, your product cannot be found. And you remember I gave you a what they call it, an energy pathway curve. You understand? There is an activation energy. The activation energy is from the ground state to the peak where your enzyme substrate complex is formed. And at that point, whenever a reaction gets to the enzyme substrate complex, it usually leads to products products formation. You agree with me to calculate the uh, product, the rate of appearance of product, that's velocity, which is also the same thing as speed. What is speed? Speed is distance, um, distance, distance over time. I need to take that again. The rate of appearance of the product, which is the velocity, is proportional to the concentration of the enzyme substrate complex. That's your steady state. Is the rate to which your product is formed is equivalent to the concentration of the enzyme substrate complex. So at this point in time, V equals to K2 then ES. So that's the interpretation of that sentence. So for us to have a maximum reaction or maximum product formation, that means the rate at which we have the highest product form will be directly proportional to the rate at which all the enzymes are being used up in the reaction. If all enzymes in the container are occupied by the substrate, that means the product formed will be very fast. So that will be the maximum velocity. That gives us Vm equals to K2 into bracket full what total enzyme used during the reaction. And so here, because there is a relationship between K2 and the equation 2 and K2 in equation 3. We need to link them together, which is V over V maximum velocity, that is Vm, equals to enzyme substrate complex over total enzyme concentration. So with the help of this equation, we can be able to measure the enzyme substrate complex that is being formed during the reaction. So at this point, I will ask you to keep that equation 4. Keep it in mind. We will still also make use of equation 3 and equation 4. So keep those equations in mind because they are very, very important, because subsequently we will also engage them in calculating various variables that is also essential to be able to determine the kinetic properties of a particular enzyme. Now, this equation, that's E plus enzyme plus substrate, leads to enzyme substrate complex. So to be able to look at the equilibrium, let me put it, equilibrium constant of this reaction, in the sense that the rate at which enzyme substrate dissociate to form enzyme plus substrate. So that means this time around it is putting the what they call it, the enzyme plus substrate as the product. So that means at the end of the day, your Km equals to concentration of enzyme times concentration of substrate over enzyme substrate complex. And with this, we'll be able to have Km equals to E concentration of enzyme times concentration of substrate over enzyme substrate complex. Now, don't forget, earlier on I've given you the value of E. E equals to enzyme total enzyme minus enzymes that binds to the substrate. So this you substitute into equation 5a. Then you'll be able to make. We can now make enzyme substrate complex the subject of the formula, and by the time you make it the subject of the formula, we'll be able to see that when you cross multiply, we'll be able to have what we have in equation 6. Have you seen it? Now this equation, looking at it, is having something similar to equation what we have in equation 4. V velocity over maximum velocity equals to Ex over Et. So at this point in time, since equation 4 and 6 share the same variable, so we equate it together, so that will be V over Vm equals to the reaction equals to concentration of the substrate over the Michaelis-Menten constant plus concentration of the substrate. Now, by the time you make V the subject of the formula, we'll be able to end up having our Michaelis-Menten equation, which is V equals to Vm multiplied by concentration of the substrate over Michaelis-Menten constant plus concentration of the substrate. And that's the curve. This is the curve, so which shows everything about it. So your Km is called Michaelis-Menten constant. It measures the affinity of the enzyme plus for its substrate. Now, in this case, when you look at equation 5a, just flip your book, you'll be able to understand that the greater the concentration of the enzyme substrate complex, the lower the concentration of free enzymes that we have. And that means consequently that's the lower the Km value. When the enzyme substrate complex substrate enzyme, when the rate at which the enzyme substrate complex is formation is very, very high, that means we will have a low Km. That means there is nothing that can obstruct the enzyme for converting it into product. This means that the lower the Km, the stronger our enzyme will be. And this is the formula: Km equals to K K minus 1 plus K2 over K plus 1. I believe we can see it in our note. So don't forget, the lower the Km, the stronger your enzyme will be. Then we also have turnover number, which is Kcat. Kcat is a measure of maximum catalytic activity. Your maximum catalytic activity means that all enzyme used in the reaction, all the enzyme active sites are occupied by the available substrate, which will eventually lead to product. Nothing is less. So we invariably substitute it to our maximum velocity, which is Vmax equals to K2 and multiply by total enzyme concentration. So what we just do is to replace the K2 with Kcat. Means that during a maximum velocity, we have maximum catalytic activity that took place. Turnover, or the Kcat, remember that it is maximum velocity over the total concentration of the total enzyme used in the reaction. From here, you can see that your Kcat, your catalytic efficiency equals to Kcat over Km. The implication of this is that whenever you calculate your catalytic efficiency and you have a range of score between whatever number times 10 raised to the power 8 to 10 raised to the power 9, it shows that the enzyme is catalytic perfect. That enzyme is fast, is swift, is spontaneous, it can be able to mature any reaction given to it. So that's all about Michaelis-Menten's equation. And for that of Line-Weaver-Burk, not to disturb yourself, Line-Weaver-Burk, don't forget your Michaelis-Menten's equation equals to V equals to Vm, maximum velocity, multiplied by substrate concentration over Km plus substrate concentration. All what you do is to find the inverse. And inverse is 1 over V equals to Km plus X Vm Vm multiplied by enzyme substrate concentration. And so you can see how 1 over V is made the subject of the formula. This can as well be equivalent to Y equals to mx plus C. From that, you can be able to see that from the video, where your 1 over V represents your Y axis and Km over Vm represents your M, and X represents 1 over X, while your X is concentration of substrate, which means it's a variable, it can change, then plus your C, your intercept, which is 1 over the maximum velocity. I believe you are familiar with that. So we also have the kinetics of reversible of inhibitors, because inhibitors also binds to enzymes. We have different inhibitors. We have enzyme inhibitors. These are what they call it, molecules that slow down or stops an enzyme from performing its what they call it, its reaction. An example of what they call it, an inhibitor is aspirin. What does aspirin do? Aspirin is used when there are inflammations in the body. So aspirin binds aspirin inhibits the enzyme that catalyze the first step in the synthesis of prostaglandins compounds. Now, that is what these compounds are produced during pain. So once aspirin inhibits them, then the person will be able to go about his daily activity without having pain. So that's the function of various inhibitors that we have, where some inhibitors are reversible, some are irreversible. For suicide is irreversible, just like penicillin binding to microbes within microbes. These are permanent covalent bond, and once it binds, it kills the microorganism. That's why we have what they call it, penicillin, and example. So examples of reversible inhibitions, we have competitive inhibitors, uncompetitive inhibitors, and mixed inhibitors. Now these competitive inhibitors, these are inhibitors that compete with the normal substrate at the point of reaction, at the active site. At the active site, they tend to what they call it, they tend to occupy they want to occupy the active site. So either the substrate bind to the active site of the enzyme or the inhibitor binds there. So that's their what they call it, that's their own Michaelis-Menten constant, where alpha equals to 1 plus inhibitor over ki, and ki equals to enzyme times inhibitor over an enzyme inhibitor complex. So that's it, your formula. You just assume that your alpha equals to that's what your alpha equals to, so you just slot in it. Now whereby uncompetitive inhibitor, the inhibitor does not compete with the active site, it goes to another place that and binds to the enzyme and affects the conformation of the enzyme, such that preventing the enzyme from binding to the substrate. That's why we have the what they call it, the alpha this time around closer to the substrate concentration. So in the case of the mixed in the case of the mixed inhibitor, the mixed inhibitor, they bind at a site distinct from the substrate active site, but it binds to either the EX, it binds to either the enzyme or the enzyme substrate. So even if enzyme substrate are formed, the inhibitor still go and binds to them, and in some cases it binds to ordinary the enzyme. So this time around you have to put the alpha beside your Km and beside your enzyme substrate in the Michaelis-Menten equation. So that's all about inhibitors, but I want you to dwell on the examples I gave you in your notes as regards what they call it, Michaelis-Menten equation. This is an example I want you to look at. This example is very, very important. So in your exam, it can be different enzymes, can be different formation, but just look at it, look at the formula, understand the formula, practice how to get the value of lane KEQ at home before you come into the exam. So by the time you get it, you'll be able to understand how you can be able to relate the formula. So all the formula used here, you will certainly make use of them. That's why that's why I went through the process of generating your generating the Michaelis-Menten equation, so that nobody will have an what they call it, excuse to forget it. Now, what are the regulatory enzymes? Regulatory enzymes are enzymes that regulate biological pathway. They are just like the knob on top of a tap. You turn it on, you turn it on. They regulate metabolic reaction, and these are being regulated. These enzymes are being regulated by different molecules. These molecules, they come whenever they come in contact with this enzyme. Once they touch the enzyme or once they bind to the enzyme, their conformational, their three-dimensional structure changes, and as such, it does affect chemical reactions. So, example, and these molecules are called effectors. Excuse me, they are called effector molecules. Now, why allosteric enzymes are, they contain regulatory sites, a distinct site from their active site. So they have allosteric enzyme have their active site, they also have distinct site. Now they bind to these effector molecules, which can either be inhibitor or an activator. So an inhibitor slows down the reaction. So that's all about enzyme regulation. You can pick the remaining from your notes. I believe it's very simple. Please try as much as possible to work with your notes. Look at the examples, understand it, understand how it is, and when you understand it, you'll be able to come out very, very well. I wish you all the best in your forthcoming examination. May we meet and may you do well. I pray earnestly that you guys will do well. All the best.